For this particular problem, it looks like a middle school conducted this survey to figure out how many students played or spent more time playing games or watching videos. And what they're asking us is, of the students who spent more time playing games, so this is a statistics problem, and right there, that's a big point right here, who spent more time playing games, of those students, what percentage were boys? So what we're going to start with, when we start with these percentage type problems, really what I like to do is make a fraction first. So if you remember a fraction, we just put the part divided by the total. So the total, they tell us right here, of those students who spent more time playing games, it looks like the students that spent playing games, that's 192 total. What percentage are boys? Of those 192 that spent more time playing video games, there's 138 of them that are boys. So if we go ahead and calculate that, we get roughly 0.719. So we'll say 0.719. Now that's in decimal form. To turn a decimal into a percentage, we just move the decimal place to the right. I was going to say to the left, to the right 2 times. So that's 71.9% of the students that played more or spent more time playing video games that were boys. Now we're going to round this up. 71.9 is not an answer, but that's really close to 72. So what you're doing here is you're finding out what the total is. In this case, it tells us of those who spent more time playing games, 192 total. How many of them are boys? That's our part. And if it was how many of them are girls, we would just change the 138 into a 54 and do the same thing. You divide this, get your decimal, and really what I just did is multiply this by 100. That's the same thing as moving the decimal 2 times to the right. Okay, so that's kind of a shortcut that I like to teach. That's pretty much all they're asking for this one. Number 11 is more of a conceptual question. There's not really any calculations that we need to do. What I want to go through is start with number 4 and move upwards. So start with answer choice 4 and move upwards. So we want to figure out which statement best describes the solutions of a 2-variable equation. Well, if you look at number 4, the ordered pairs must have y equals 0 for one coordinate. That makes no sense. There's nothing about any equation that says y equals 0 must be part of the coordinate. Same thing with number 3, answer choice 3. The ordered pairs must have x equals 0 for one coordinate. There's nothing that we ever teach or that is ever part of what we teach about x being 0 or x needing to be 0 to be a solution to a 2-variable equation. 3 and 4 are just softballs that they threw out there, absolutely, that really sound like they could be correct, but they're not correct at all. Okay. Number 2, the ordered pairs must lie near the graphed equation. That's really, really tempting. But what I'm going to tell you right now is that the graphed equation is quite literally, it's all the solution points that lie for a particular equation, if that makes sense. The graph of an equation is all the solution points of that equation. It's all the solutions to that equation. That's what a graph is. So it wouldn't make sense that the ordered pairs would be near it. It would make the most sense that the ordered pair must be on the graphed equation. That would mean it's part of the solution of the equation. That's what a graphed equation is. If I graph an equation, that graph that you see, whether it's a line or a parabola, that's all the set of data points, usually x, y coordinates, that satisfy whatever equation we're talking about. So the ordered pairs must lie on the graphed equation, have to be on it, not near it. They must lie on the actual graphed equation for it to be a solution to a 2-variable equation. Number 12 is asking us, okay, given this particular expression, which of these is equivalent to that? AKA factor the quadratic expression. That's all we're doing for this one. Now, what I'm going to do is the x factor method. That seems to be the most popular. That's a bad x. But we do factoring by grouping. We could do the box method, whatever you're comfortable with. It's purely up to you. They're all very similar as well. So really what I like to do is I'll put the product up here. So AC, A times C. So A is the coefficient on the squared term. That's just a 1. C is this value right here. 1 times 24. That's just 24. Our B value is -10. Now, what we have to do is come up with 2 numbers that add to give us -10 and multiply to give us 24. And I'll give you a hint. If you know that we're multiplying 2 numbers but getting a positive, but those same 2 numbers we're adding to get negative, the only way that we can do that is if we have 2 negative numbers, okay? And I'll let you go through the motions of writing out your factor tree if you want to do that. But in the end, you should come up with a -6 and a -4. -6 plus -4 is -10. negative 6 times negative 4 is positive 24. Now, because a is just 1, we can go right ahead and drop them into their own binomials. X minus 6, x minus 4. Okay, now if a was not equal to 1, we would have to go a step further. If you're not comfortable with the x factor method for that, when a is not equal to 1, we can definitely use, again, factoring by grouping or the box method. They're all three very legitimate. This x factor method kind of came on the scene and took over because it actually is pretty convenient for a lot of things. So long story short, if we go through, this is our final answer for that. If you want to check your work, you can FOIL it out. X times x, that's x squared. X times minus 4 plus minus 6 times x, negative 4x plus negative 6x, that's negative 10x. Negative 6 times negative 4, positive 24. Always check your work on these because it doesn't really take too long to go back and FOIL it out. So that's all we have to do for that one. All right, so we've got a fun looking problem here where we have two quadratic functions, f of x and g of x, and we need to figure out which statement is true about them. Now we have the graph of g of x and we have the equation of f of x, and we're just going to go through and see which one of these is true. Now I wrote two different expressions up here. This is just the standard form of a quadratic. This is just the, it's a couple of things actually. It's the x coordinate of the vertex of a quadratic, and it's also the axis of symmetry. We're not going to do the axis of symmetry here, but I do want you to remember this. You definitely need to know that. That tells us the x coordinate of the vertex. The reason why we need that is because the first part is saying the minimum value of g of x is greater than the maximum value of f of x. So we need to find the maximum value of f of x, aka the vertex. So I'm going to start right here for that. I'm going to use our values here. It looks like b is negative 4. So x is equal to negative 4, so double negatives cancel out, over 2a. A is just a negative 1, so over negative 2. So x is equal to negative 2. So our vertex for f of x occurs when x is negative 2. Now let's figure out what that is. If I plug in negative 2 for x into f of x, we get this right here. I'm just going to write it out. So we get a positive 4 times a negative, so negative 4 minus 4 times minus 2, that's positive 8, minus 4 again. So it looks like these actually just cancel out to 0. So our vertex, which is going to be the maximum for f of x, occurs at negative 2, 0. Right here. And it's downward facing because a is negative, so it's going to look something roughly, very rough, like this. If you look, this is saying the minimum value of g of x is greater than the maximum value of f of x. Well, that's not true because the minimum of g is negative 4. The maximum of f is 0. So that's opposite. The minimum value of g of x is actually less than the max of f, if that makes sense. so it can't be 1, okay? And if you're not comfortable with what I just did, this all stems from finding the vertex of a parabola, and you definitely need to remember this. This gets us started. That gives you the x coordinate of the vertex of a function. So let me get rid of some of this so we have a little bit more space to work with. We know it's not 1. So let's get rid of that. We know it's not 1. Let's start with 4. F of x equals g of x when x is equal to negative 4. Well, if I look at the graph, when x is equal to negative 4, 1, 2, 3, 4, we're way up here. It looks like whatever that is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So g of negative, that's a g by the way, g of negative 4 is equal to negative 12. Now we need to find out what I can't write today, f of negative 4 is. So we just plug in negative 4. So negative 4 squared minus 4 times negative 4 minus 4. Again, can't write. We have positive 16, but times the negative. So negative 16 minus times minus, that's plus 16. So those cancel out to 0, and then minus 4. So f of negative 4 is equal to negative 4. So this can't be true because negative 12 is not equal to negative 4. Okay, so it can't be 4. What I will show you is number 2, just to save time because we're running out of time. I didn't want this problem. I saw this problem. I knew it was going to be a little bit longer than the others. But if you look, f of x and g of x have the same y-intercept. Well, if you look at g of x, the y-intercept right there, it crosses the y-axis right here at negative 4. And if I look, and again, another way of thinking of the y-intercept is it's the y value or the function value, same thing, when x is equal to 0. So all we have to do here to find that y-intercept is plug in 0 for x. Anywhere I see a 0, anywhere I see an x, I'm going to plug in 0. So 0 squared, that's 0. Minus 4 times 0, that's 0. Minus 4. 0 minus 4, that's just negative 4. So that's true. F of x and g of x do have the same y-intercept. Now for 3, for us to prove, I'm not going to prove it here just because we're running out of time. For 3, all we would have to do is, we know the roots for g of x. It looks like it's positive 2 and negative 2. We would have to factor this into 2 binomials and then solve for the roots. Okay, you can do that on your own. I encourage you to try that just for practice. But for our purposes, because we're running out of time, I want to skip that and show you why number 2 is the correct answer. All right, number 14 is a classic exponential equation question that they love to ask, whether it's the value of a motorcycle or a bank account with a particular interest rate. They love these types of problems, and they will try and trick you every single time. So let's go through these ones. What I want you to remember is that in this particular case, imagine the value of a motorcycle. It's actually decreasing after we purchase it. So this is actually represented by exponential decay, which looks like this. In this case, t represents the number of years after it was purchased. And if you remember, a is always the initial value. Okay, so the initial value in this case for these time problems is almost always when t is equal to 0. All right, so if I look at this expression and I plug in, so we have 12,000 times, my zeros sometimes turn into rectangles, 12,000 times 0.75 to the 0. Anything to the 0 power is just 1. So that's just 1. So I want you to imagine at t equals 0, that's basically when I purchased it. If I just purchase it, time, you technically could be like, well, it's 0.1 milliseconds. But no, we're not doing that. Time equals 0 is right when I purchased it. What you just found out is if I plug in 0 for t, that's the initial value. And it looks like that's exactly what number 2 is. It's the motorcycle's cost exactly when you purchased it. All right. What I do want you to see, this one is tricky. They try and trick you with that because you see the 0.75 and it's tempting to think, well, it's decreasing by 75. No, it's actually decreasing by this amount, 1 minus 0.25. That would give us 0.75. And if you remember, our rates are always in decimals, but if I put that in percentage, remember I have to move the decimal 2 times to the right, that's 25%. So it's decreasing at a rate of 25%. And also going right along with that, number 4, they try and trick you. I looked at this and I had to double take myself. I was like, wait, can it be 4? Oh, it's 0.25%. It's not decreasing at 0.25%. It's decreasing at 25%. Okay, but we wouldn't even have to get that far because once you look at number 2, the motorcycle cost $12,000 when it was purchased. All you would have to do to check that answer is plug in 0 for t. That's the initial value. That's exactly what they're asking here in this case. When it's purchased, time is equal to 0. If we evaluate that, that's how we come up with 12,000 being the initial value. Okay, and you don't even have to do that, to be honest. If you remember your exponential equations, this value right here is always the initial value. Okay, but I do want you to know that we can plug in 0 for t, and that gives us the initial value as well. Okay, looking at 15, it's obvious we've got a quadratic equation that we're trying to solve. I know it's really tempting. A lot of my students would want to take this and FOIL it out and get everything to the same size so that it's equal to 0 and try and factor that. We don't want to do that here. That's a lot more work than we have to do in this case. What I would highly recommend is just get this square term by itself. Get that quadratic term by itself. Let's isolate that. So by doing that, or to do that, to start, I would add 2 to both sides. So get that 2 to the other side. Now from here, if you remember, I need to get rid of this square term. All I have to do is do the inverse of that, which is the square root. And now here's also where a lot of my students will mess up when we first start these, is when you take the square root of something that's being squared, you get a plus and a minus. So plus or minus, square root of 9 is just 3. So for both of our answers, notice that's 2 different things. Let me move this down just a bit. So when so we'll have, this is the same thing as saying x plus 4 equals positive 3 and x plus 4 equals negative 3. So we just subtract 4 from both sides. X equals negative 1. Over on the right side, we get x equals negative 7. So negative 1 and negative 7, those are our solutions for this one, and it looks like 3. So all we had to do, again, was just isolate this square term. And I would recommend this almost all the time. If you have this quadratic term going on and you're trying to ask you for the solutions or solve this equation, isolate that quadratic, bring whatever's on the outside, bring it to the other side, and then square root both sides. Sometimes you will end up with a radical. That's just kind of the nature of the beast of that, but it's much quicker than if you were to FOIL everything out, bring everything to one side, try and factor it. In this case, it would factor, but it'd be really difficult. Okay, it's a lot more work than you need to do, and it takes up a lot of time. Okay, so that's all I want you to do for these ones. So I first saw this one, right when I looked at it, I was like, this is just going to be fun. So basically, if you see this, what I tell all of my students, if you see 4 expressions, I automatically want you to think, okay, let's see if we can factor by grouping on that one. And what I mean by that, if you're not comfortable with factor by grouping or factoring by grouping, we're going to do that right now. Since there's 4 terms, we can group them into groups of 2. So I'll put these 2 together and bring this minus, make sure it's inside the parentheses. So what you want to do from here is take each of those 2 terms now that have their own parentheses, and you want to look at them individually. So let's look at this other, negative 4x cubed plus x squared. What do they share in common? What's their greatest factor that they share in common? It looks like I can pull out an x squared from that. And if I do that, I'm left with a minus 4, and I'd still have an x. The x squared just becomes a 1. Now, if you look at negative 6x plus 8, what do they share in common? It looks like they just share a 2. You could pull out a negative 2, but let's just say we pulled out a, actually, let's do that. Let's pull out a negative 2. And what I'm left with, this negative 6 becomes a positive 3, and we still have that x attached to it. And if I pull out a negative 2, if I factor out a negative 2 from a positive 8, I get a negative 4. Now, let's see if that's one of our answers. I see we pulled out an x squared. We got a negative 4x plus 1, minus 2, 3x minus 4. So that's equivalent, okay? But that's not the answer. We want to know which one's not equivalent. I know that's just like, oh, great. So what you want to do is look and see, all right, well, if I took, it looks like for number 2, what they did is they left the 8 completely by itself. I don't just have to factor, or when we're doing factoring by grouping, I could group 3 of the terms together if I wanted to. I wouldn't want to, but I have to. I kind of here to check and see if it works. If I group the first 3 terms together, if you look at those 3, what's the only factor that they share in common? To me, it looks like an x. If I pull out an x, what I'm left with is a minus 4 x squared, that's an x, minus 4x squared, plus x, minus 6, all in parentheses, and there's still that plus 8 on the outside. Now let's see, is that what they gave us for this one? X times negative 4x squared, it looks like a minus x, right? Plus 6. But we didn't get a minus x, because if you look x squared, if I pull out a positive x, I still get a positive x back. That's not right, okay? It would not be 2. So, well, since it's not 2, it's not equivalent to this. That would be our answer. That's what I meant to say. But what that does mean is that 3 and 4 are equivalent to this. And all they did for these ones, for number 3, what they did is they took these 3 terms and they factored that. And that happens to factor into this 2 binomials multiplied together. And they took 4, and it looked like they did the same idea, but they didn't pull out, or they mixed and matched. Okay, so they swapped the 8, and it looks like they swapped the x squared. Okay, because we can put these in any order that we want. Long story short, remember, when we're factoring by grouping, we don't just have to put the 2 together, like the first 2 and the next 2. That's normally what we're doing when we're trying to when we're actually trying to factor them. But if we're just trying to rewrite it, we can group them in any order that we want. I could put the first 3 together like this and pull out a common term. I could put the last 3 together and pull out a common term, and it's still an expression that's equivalent. Okay, so that's the main big term here. Now, why would you want to do that? You probably wouldn't want to do that in this case, but they're just asking which of these is not equivalent. Okay, so we have to kind of run through all the possibilities, as fun as that is. So it turns out that this is not purely because they missed a negative here. This should be a positive, like we got right there. Before we get started on this one, I'm going to type out 2 things that I need you to remember. Linear equations change with a constant. Wait, that's going to be redundant. Have a constant rate of change. Exponential equations change by a constant factor. Okay, when I think of factor, I want you to think of a percentage or a decimal or a fraction. Okay, so with that in mind, that might not make any sense to you for some of you guys, but for others, you may be like, oh yeah, I remember that. Linear equations have a constant rate of change. So if you remember, if I gave you like y equals 2x plus 4, every time I increase x by 1, y is increasing by 2, because 2 is the slope. But that's the constant rate of change. It's constantly changing by a rate of 2 every time x increases by 1. Okay, but exponential equations, on the other hand, let's say I had I put in a certain amount of money into a bank account and it triples every year. That means it's multiplying by 3 every single year. That's not a linear equation. That's actually an exponential equation that looks like this: 3 raised to the power of x, where x could be the number of years. That's what that means. Okay, so be very, very careful. Even though it's double, you might think, and the reason why I brought in the triple is because if you look at number 2, it's saying, and I'm starting with number 2 just for no purpose, I want you to see it, but it's doubling every 5 years, and you might think, well, it's constantly doubling. That's kind of like a constant rate of change, right? And no, constant rate of change means it's changing by the same amount for every given certain amount. Now, if it's doubling every single year, I could start with 2, next year I'd have 4, next year after that I'd have 8, and then 16, and then 32, and look what happens. The first rate of change was 2, the next rate of change was 4. Right there, I want you to think, well, that's not constant. It would be, if it was constant, it would be changing by 2 every time, or changing by 4 every time, right? So right there, if it's doubling, it's not a constant rate of change, that's actually an exponential rate of change. So that can't be a linear equation because it's not a constant rate. So 2 is out. Same thing with number 1. It's decreasing by 10% each year. We kind of did a problem like this maybe 2 or 3 problems ago with that one car that was worth like $12,000. It was decreasing by like 25%. It looks just like this. This is an exponential decay problem where we have 1 minus r, where our rate is just 0.1. And this would be raised maybe to the t power times whatever our initial value is. 1 minus 0.1, that's 0.9. If you look at this, 0.9 raised to the power of t, or sometimes we won't use t, we'll use x, automatically I want you to think, oh wait, that's not linear, that's an exponential function. Any value raised to our independent variable, usually it's t when we're doing these problems, but it could be x. That's a dead giveaway that is definitely not linear, that's exponential, so it cannot be 1. Now let's say we had 2 liters of water are evaporating every single day. That means, let's say I started with 20 liters on day 1. On day 2, I lose 2 liters, so I'm down 18. Next day, I lose another 2, I'm down to 16. You can see the pattern here. I'd be down to 14, and then 12, and then 10. If you notice, every single time I increase the day by 1, my liters are decreasing by 2. That's the constant rate of change. That's a linear equation, okay, because the change is a constant rate of change. Okay, and then just so you can see, number 4, if my the amount of caffeine in a person's body is decreasing by 1/3, again, right there, constant factor, that's a constant fraction. So let's say I started with, if I started with 21, if I'm decreasing by 1/3, I have 21, and 1/3 of 21 is just 7, so I'm losing 7, so I'd be down to 14, and then I would lose whatever 1/3 of 14 is, right? 14 thirds. Well, if I decrease by 7, and then I decrease by 14 thirds, that's not constant. These are 2 completely different numbers. They're close, they're kind of close, but they're not the same, okay? So right off the bat, I want you to look at 3 and be like, oh, 2 liters, boom, done. There's no percentage, there's no doubling, tripling, halving, anything like that. There's no, oh, it's decreasing or increasing by 1/3 or 1/2 or 1/5. If you ever see it, it's increasing or decreasing by a percentage, a decimal, or fraction, I automatically want you to think, all right, that's probably an exponential equation. That cannot be linear. Okay, linear means constant rate of change. So we're trying to find the range of this particular function, and I want you to put your eyes right here. That tells us, okay, we're doing absolute value. If you don't remember what the absolute value function looks like, I'm going to show you what just the normal parent function looks like. The absolute value of x equals y looks just like this. It's your V shape. It looks like that, and then it looks like that. It starts at 0, 0. Now, if you remember, this is actually a function, this is actually a question that involves the absolute value, and it also tests your ability of doing function transformations. So this +3 actually takes this graph and shifts it to the left 3 and down 5. 1, 2, 3, 4, 5. This is going to be a very rough graph, but left 3, down 5, it would be right about here. And it would look something like this. Very, very rough draft. And I forgot the arrows on this. It goes infinitely in those directions. So this red graph, that's our graph of the absolute value of x plus 3 minus 5. Now what we're looking for is the range. Remember, the range is just all the y values, all the function values. What's happening is, if you look, and we always go from least to greatest, what's happening is we're starting from -5. And if you look, if we were to travel up, our y value, that's an arrow by the way, our y values are going up infinitely. There's no stopping. It continues to go up and up. That's what these arrows mean. It never just kind of reaches a point and says, no. It always goes up. Okay, so it's going from -5 all the way to positive infinity. Now, if you notice on the infinity, they're all parentheses. We always put parentheses or open brackets around any infinity or negative infinity, always. But -5 is actually included in the function, okay? Because if I plug in -3 for x, -3 plus 3, that's 0. Absolute value of 0 is just 0. And 0 minus 5, that's -5. So that's part of our function. We have to include that. That's what this bracket means. It means the inclusive, it just means inclusive. So if you see the square bracket, that means -5 is included in the range. Okay, so our only option would be right here. They try and trick you with these threes. Those threes only have to do with this new vertex, if you want to call it that. So they try to trick you with that one. And they try and trick you with this one by putting an open bracket. But remember, when we talk about the range, in this case, we definitely include that -5.